Welcome everybody, welcome everyone out there on YouTube, on Twitch. This is Building Stuff with Nova. This is your virtual makerspace, your mastermind, your ideation laboratory. For those who do not know, this is a place where we build together. My name is Dr. Nehemiah Mabry. I'm your host, but you know what? You can call me Dr. Nee. I want to give a special shout out, y'all, not only to our returning community on Twitch, the building community, as I've been affectionately referring to us, but also our friends on YouTube. If you are joining us for the very first time, whether it be on Twitch or on YouTube, go ahead and drop in the chat where you're joining us from. I'm going to be looking at the chat. We've been on YouTube a couple of other times before, but today I want to make sure I give a chance to give you a shout out. So if you're joining us from YouTube or on Twitch for the very first time, let me know where you're joining us from, because this is something that we hope to build a bigger and bigger community around. We've been doing all types of things as it relates to engineering. We've been gaming, we've been building things. Oh man, we have some field trips lining up. I'm telling you, you don't want to miss the field trips. And we've been doing guest interviews like we have today. So again, happy to have you with me. I am super happy to see you all. Shout out to the Opal guy over on YouTube. How you doing? Herself. We see our returning folks. Kajo, good to see you. Excited for today's streams. Me too, the future doctors. I'm very excited. As you can see, I have on my superpower shirt. That's right. It's the Nova swag. So in case you too are looking for some superpowers, I encourage you to go check out some of the Nova merch. I had to wear it today because I have a very high-powered guest with me today. That's right, TK Skagen. We have a great guest. So even though you're joining us from Seattle, Washington, I see you on YouTube. We're right here. I'm presently right here in North Carolina. My guest, we're going to bring her on in just a little bit. She's going to tell you where she's joining us. But let me tell you really quick, Andrew. I see you in the chat. Shout out to Phoenix, Arizona. I want you to understand something, that we're building something here on this channel. It's not just in the name. It's literal. We're going to be doing this every day, pretty much at 1 p.m., all the way until the fall, where we're going to have a finale. What's the finale, you might ask? The finale, and this is especially for my new folks, we're having a 4-day engineering-themed escape room. That's right. Never been done before. We're using our audience, our community, primarily over on Twitch. And so if you're on YouTube, we enjoy you to go ahead in future dates to hop us and join us on Twitch. But we're building an escape room with your help. So we've been ideating. Yesterday, we had Mike from Trapology, a wonderful, phenomenal partner from Boston, to help us ideate puzzles around aerospace engineering. We're going to be doing structural engineering. We're going to be electrical and computer engineering, even energy. We talked about fusion energy yesterday, y'all. So I want you to understand this is the place for you if you're interested in just tinkering and playing. There's no qualifications. All you have to do is come and be a part and have a great time with yours truly, Dr. Nee. Let's see what other shout outs we got going on. We got Johnson City, Texas in the building. We see you. Southern Idaho. I love it. The Oval guy, shout out to you. We got Priscilla. All right, everybody. Connecticut. Yes. Used to teach hands-on science to K-12 teachers. Shout out to you. Love to have you here. I hope the audio, yes, the audio, our first stream was a little shaky, but I think you all can hear me well. As a matter of fact, shout out to the Twitch community. Let me know if you can hear me. Just type the number, the letter Y. I'm shouting out to especially the building committee. They know we go through the ups and downs, much like the engineering design process itself. We iterate, we test, we try things, we make it a little better, and we get better and better and better. So type the letter Y. Shout out to the Twitch community. I see you, Artsy Chickadee, super excited about the escape room. Me too. Me too. You are an elementary arts teacher and you want to try creating an escape room. Then you have to join us. We're going to tell you about what we have coming up, when we're going to have our escape trapologist, Mike Tremblay, join us again. But you have to join us because we're going through all of that. Shout out to you. Welcome to the channel. Thanks for the Y, Bill. I see the Y. So that means that you all can hear me. Great. Since you can hear me, let's do something. Let's get our agenda on the screen. I'm gonna let you know, pretty straightforward agenda today. Yesterday we did trapology. We did a lot of escape room ideation. On Monday we played Kerbal Space Program. But today is the day that you are fortunate to be with us, because we have none other than Dr. Melissa C. Lott. That's right. Dr. Melissa C. Lott is someone who I was fortunate to meet not that long ago, who has an incredible passion for all things science, engineering, and climate. So we're going to bring her on in just a second, but I want you to understand that we're going to be doing something unique. This is not going to be your typical interview, and I'll explain it more in a second, but we want to understand what type of climate implications does your morning cup of coffee, or I like to say my morning sweet self-love routine? What does it have when it comes to the climate implications? So that's what we have today. And then again, for those of you who heard that tidbit about the escape room, I'm going to talk about when we have things coming up, what's to come, when you can join us again for that ideation process. But I need you to buckle your seat belts and get ready as I bring to the screen my guest for today. My guest, none other than, let's drop some emotes, let's drop some hearts, let's drop some celebratory little images, whatever you're doing. That's you on YouTube as well on Twitch. And put our hands together for my guest today, Dr. Melissa C. Lott. Let's see it in the chat. We see the hearts. A la carte Germany. I see you. Melissa, you're here. We see you. Go ahead and wave to the people, Melissa. We get to see you.
I love this. This is great energy. I love this. And the escape room, because we talked about it. That's going to be really awesome. I can't wait to see it.
Oh man.
I can't wait to see everyone get together for that. That's going to be epic.
You have no idea, Melissa. We've already been ideating with like different ways we're going to do, like model a rocket launch in the middle of an escape room. Have you seen a rocket launch in an escape room? I don't know. I haven't. You know what I mean? We're going to do that.
I've seen a rocket launch.
Yes.
And separate, but no, not together. Oh my gosh, I got to see this now. I tell you what. I love something about engineering, which is we're always trying to improve processes and figure out how to make things better and how to create stuff that's never been done before. Yeah. I know Stephanie on the team here is actually sending us a note right now and talking about how we're building stuff in the background as this thing goes on, and how we might need to switch some platforms in 4 minutes. So it's we're always creating and we're always building. And I absolutely love that because it's like, well, we've never done that before. We've never launched a rocket.
I know. Well, I want you all to understand something. Here's the thing, Melissa, because we're going to make sure we have that break when we switch platforms. But here's the thing I want other people to know, that this is one of the most Twitch, YouTube, the most like meta projects I've ever been a part of. So
awesome.
I've shared that with you. Like, I'm an engineer by trade, have my degrees. I know you have some engineering degrees that we're going to get into in just a little bit. But it's like we're going through the engineering design process as engineers talking about engineering. Like, I don't even know if you get more meta than that.
No, and it's like every time you're doing it, you're like designing something, you're solving something, and then you're immediately switching to like, okay, how do we do it better next time? How do we make this more efficient? How do we like change up some material, something to like see if we can get something improved? And it's continuous, which probably drives our friends and family nuts sometimes. But as fellow engineers, we can love this. We can love this part of the whole process for sure.
Absolutely. And you know what? You have participated in several Nova projects, right? And I want to make sure I get a chance to like highlight some of these. But if you can, give us a quick timeline, maybe just a quick like 2-3 minute timeline of how you got from engineering, which is like a similar background we share, 2 different disciplines, but maybe even earlier than that. Give us a quick 2 to 3 minute timeline of your path to where you are today.
Yeah, so I grew up in a military family in the US. And so we moved around a lot. I saw a lot of different parts of the country, early in my life, which was really fortunate in a lot of ways. I got to experience a lot of the different cultures we have right here in the US. And within that, I got really into, I didn't call it sustainability at the time, but I get into, okay, I'm living in this community. How do I leave it better than when I got here? How do we improve things? How do we make it healthier? All that stuff. And I called that sustainability later. But when I was like a teenager, it was just things I thought about, looking at the ocean or the beach when we were, stationed in California, or, looking at the local park or the local nature preserve or wildlife preserve. And so within that, what I quickly figured out was that the cause of so many of the issues I wanted to solve was actually something called the energy system. So I was like, well, that's where all my solutions are. I got to go deep, and I got to go deep into that. And I discovered that pretty early when I was a third year in undergrad. That's when I figured out what energy was about. I mean, I flipped a light switch. I knew the electricity, it was a thing. I understood those pieces of it, but it's like, where does air pollution come from? How is water affected by this? Like all that stuff, learned about climate change. And I went, wow, as an engineer, what do? We identify problems, we figure out what tools we have in our toolbox, we create new tools when we need them, and we use them to solve those problems. And I was like, perfect, this is the thing I'm going to work on. Like I can actually be part of the solution for the thing that I really care about, that I've been drawn to since I was little. But
you were doing
the first time I got into this topic.
Student though, right? Like you were mechanical engineering at the time?
I was something called biological systems engineering, which is basically biochemical engineering. So I did all of the stuff that all the mechies, all the mechanical engineers did. I was in classes with the civil engineers, but I also did like organic chemistry and biology and understood that interface between, life systems, people, and the machines we're creating. And so I studied at University of California, Davis up in Northern California.
Yeah. Shout out to California. Let us know if you're in the
it was
chat.
great.
Go ahead.
Absolutely. West Coast, and got to know that whole system. And it was really just a fascinating way to step into it. I stepped into electricity first. So like back up for a minute. Step number one, what is energy? We think we can all define it, right? Like I bet we could drop a ton of definitions in the chat. Energy is this, energy is that.
Yes.
For me, energy is a bunch of different systems that we live with every day. It's like our power plants, it's our homes, and it's also our transportation, and it's our industry. So like how we build the things that we want to use in our lives. And so when you think about that, you realize that energy touches every piece of our lives. You cannot get away from it.
Yeah.
And so it's just one of those things where in California, I was there during Enron, during blackouts and price spikes and all kinds of craziness. And you just suddenly realize that this invisible thing that just kind of enables a lot of stuff in your life is actually really tangible. And as an engineer, those cycles I learned about in thermodynamics, they're living over there in a 5-story tall, massive facility with huge turbines in them, those types of things.
Well, here's the thing. I want everybody to understand we're going to get deep and dirty. We're going to get our hands dirty in this. And I want you to hold that thought for a little bit, because what we're going to do is allow Melissa and I to kind of get set up here behind the scenes. Shout out to everybody, again, joining us on YouTube and on Twitch. Melissa, you're getting a lot of love, and I know you'll be able to hear this in the background. But as I go to just my quick primary layout, as we get things straight behind the scenes, I want you to understand something, y'all, that here is a place where you can ask questions as well. This is an interactive sort of like process, right? And we've got Melissa here, not only on Twitch, not only YouTube, but here on Zoom. We're going to get the new link in a second. But as we talk to Melissa, I'm going to periodically pause. I'm going to allow you all to make sure you ask your questions. I'm going to make sure you can answer these questions. I mean, shout out to the people even in the chat. I want you all to understand that even now, you can drop it in here. I might not get to it live, but I will come back to it. I see some of the people who've told us that they say, hi, Melissa, good to see you. Yes, your students will love that. Everybody on YouTube, Priscilla, get to see you. Michael, get to see you. Artsy Chickadee. All right, we're getting things straight in just a second. But I have a small, really quick like intro clip I want to put on the screen really quick for you all. An intro clip for Melissa. It's going to share a little bit of what she got to do in a part of a Nova documentary called Chasing. Put it in the chat. Nova, you can tell me Chasing Net Zero, Chasing Carbon Zero. I think there's a particular Nova documentary that you can find all about the work that she does. Not only that, but the work of other people as a part of it. But we have a clip right now we're going to put on the screen that I want to make sure that you all are able to enjoy with us as we prepare to bring her on and we get down and dirty in terms of breaking apart our appliance. But get your questions ready. Everyone get everything ready to go. Sorry about that, guys. I got a little notification here. Okay, here we go. We're about to play this clip first, and then we're going to get Melissa here on the screen with us for our interview. Let's see if my clip's ready to go.
Hold on, I'm sending Melissa the link.
All right. Here's the clip.
Reaching zero tailpipe emissions from cars and trucks will take some time.
So we're headed towards net zero, but we are on the local train. Need to hop over to the express.
Melissa Lott is an engineer focused on energy.
So I take the energy used in this train. Let's just
really focused.
Metal, plastic, paper, glass in the windows.
Everywhere she looks, she sees embedded carbon.
So I could probably figure out the carbon footprint of that.
It's a superpower.
20 people average per car.
Or is it an obsession?
I see energy in everything I'm looking at. I actually enjoy it, and I don't even notice it that much. It's just something that I'm running kind of in the background all the time.
So as it turns out, this obsession actually comes in handy in my line of work.
That's right. It comes in handy in her line of work. And we're going to see if we can get her back here in just a second. I think she's joining us right now via Zoom. There she is. Melissa, we're going to bring you back
Hey,
here
Nee.
on the screen. Right about now. Thank you all for bearing with us. Here we go, Melissa. All right, let me know if you all can see Melissa again. We're going to bring her back up on the 2 screen. Look at that engineering design process in motion, Melissa. As everyone
We're building
is seeing
stuff
right
together,
now.
man.
Right there, right?
We're
This
building
is
stuff
meta.
together. I love it.
I love it. All right, so let me take you through a nice scenario, Melissa, if you will. All right. Thank you, Nova. Shout out to Nova on Twitch. Says put the full Chasing Carbon Zero film can be found. By the way, if you're joining us on Twitch for the first time, now's a good time to hit follow. And everyone on YouTube, I'm about to set the stage for you. You're more than welcome to hop over to Twitch and to hit follow there as well, because that's where we're doing this every day. But let me set the stage for you really quick. Here we are, Melissa. I believe in self-care, right? We believe in self-care. I'm gonna do a nice little overhead screen share thing here so you can see. I have 2 camera setups, and every morning, I wake up with sometimes, the need to set things off on the right foot. You understand what I'm saying? And for many
Absolutely.
people, this starts with a nice, let's say, dark hue liquid in the middle of a mug. And matter of fact, this is the mug here. I just shout out, they got Mabry Mill on it. Mabry for yours truly, Dr. Nehemiah Mabry. This mug carries something that really just, I don't know, it automatically sets my day off right. But the way to get that dark hue liquid inside of this mug, I come over to, this is hypothetical, the hypothetical scenario, Melissa. I come over here to this nice coffee bean grinder, right? Coffee bean grinder.
Nice.
I'm not going to show too many, I don't know, specific coffee beans. I don't want them to think Nova is biased to any particular brand. But at the end of the day, the point is this. I put nice, small little coffee beans in here, right? You can see that. You can see that bean. Let me see if I can do it. I got mine overhead. Right there, right? That's just one. And I get out some nice grounded coffee beans, right? In this appliance. From there, I'm able to come over to my coffee maker. I think you see where I'm going, all right? I take my nice grounds and I put it into my coffee maker. And from there, I'm able to produce a nice warm, not scalding, if you will, right? We don't want it scalding, but a nice, perfect warm temperature of that wonderful liquid that then eventually goes into my mug. I finish it. I make sure it's done. I pour it into my cup. I take this dark goodness, and if I really have time, Alyssa, I take a sip and I take this little massager. And give myself a nice back massage. That is at least until my girls get up. Here's what I want to ask you, though. I've watched the documentary. You said, as everyone saw from the introduction, that you like to look around and you see things and you wonder what type of carbon footprint do they have, right? Like what type of impact do they have on the environment? And so what I thought we would do, we chatted about this, we would break down something. I think we're leaning towards the coffee maker and try to throughout the process, discuss sort of the impact it has on the environment. So should we go with the coffee maker, or, I know I threw the massager in there out of the blue. I'm just want to make it a little more realistic. Sometimes when I'm really feeling good, or the grinder, where you want to go. And then we can just dive into this through our interview.
Oh, this is hard. But I'm going to say the coffee maker, but can I have a mulligan or a asterisk footnote?
Yeah.
Can we come back to the massager later? Cause I'm really curious. I've got questions.
Yes,
I've got questions about what's inside that. So
It's
can we put that
massager,
one
the
in a
overhead
pause?
cam, right? This is may not be your typical massager. Right? There are different ways that you can get a massager. But we'll come back to it. We'll come back to it, Melissa. Coffee maker it is. Chat. Okay,
cool. Because the coffee maker is where your morning brew is made. I even use it. I drink tea. I even use it just to boil my water, especially when I'm traveling, to get hot water in the morning to make my tea. So,
really? So you're a tea drinker. I should have did tea, right?
I am.
Okay. All right. Well, listen.
No, but coffee's great. It smells amazing. I don't drink it, but I love the smell.
It does. And shout out to YouTube, shout out to Twitch, chat. I want you all to know that this is an actually used coffee maker. And what we're going to do right now, I'm going to start taking this apart. I'm going to deconstruct it. And as we pull things out, we have a little filter here. These are the things that are supposed to come apart. A little filter. obviously there's a lot of plastic, and I have some tools right here next to me, and we're just going to break it down. Melissa, as I begin to do that, let's just start with like your first thoughts. All right. What are your first thoughts? As you can see, the easily deconstructible parts of this coffee maker, as I get my screwdrivers and things like that. What are your first thoughts? Let us know.
Yeah, so you know that like I spent a lot of time getting to something called net zero, studying how to get to net zero. So net zero is where we find this balance of like those greenhouse gas emissions we put into the air and the ones that we pull out, so that we can stabilize the climate, keep people healthy, keep communities safe, all that. And so within it, in my mind, I'm already thinking about what I think is going to be inside this thing when we take it apart, and then also how we use it in its lifetime. Because when you talk about getting to net zero, solving climate change, you have to think about getting the greenhouse gas emissions out of every single step. So it's like step one, what you just did, you took out that filter, and it's like, all right, what's that mesh made of? There's obviously plastic from what I can see, but like, is that metal mesh? Is that what is that? What is that?
This is like,
does it look like metal?
Yeah, it's like it feels like some sort of wire.
Yeah, it's probably a metal wire.
Yeah.
And you probably put a paper, when you use it, you probably put a paper filter like inside of it, and use the.
Chat,
I know enough about coffee to know that.
Make sure y'all can see that. So are you saying that the materials and the paper and the wire, how does that relate to to carbon?
Yeah, for sure. So when we think about like carbon, there's different things. There's direct emissions. So like emissions of greenhouse gases that happen when you're using this coffee maker, like when you're actually using it, when you plug it in the wall, and like, is it actually producing emissions there? There's not a ton when it comes to this coffee maker, but there's a lot of indirect and life cycle emissions. And I can like talk through those, but indirect is like, that's an electric plug, right? You're plugging this into the wall. You're not like firing this up with natural gas or something. So you're plugging it on the wall, and behind that, at the end of many, 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 many long wires, there is a power plant. And that power plant could be natural gas, it could be coal, it could be nuclear, it could be renewables, it could be hydroelectric, so water power, it could be solar, it could be wind. But I'm thinking about, okay, step one, what's immediately in this coffee maker? And then where did those things come from? So what I'm going to bet when you start taking this apart is that in addition to the wire on the filter, you're going to find a bunch of wires inside. I mean, you've got an electric plug, so like, I'm going to guess there's already some copper in there. It looks like there's some rubber. There's probably some aluminum, but let's start opening it up. Let's like see what we're seeing. In my mind, I can picture what I think is there, but I don't actually know that it's there. So, you got to take it apart and deconstruct it and see what you have.
We're definitely going to find out, Melissa. We're definitely going to find out.
That's awesome.
Shout out to somebody in the chat who said that. Why is this construction making me nervous? Someone is getting a little nervous. I don't know. Don't worry. It's not plugged in. We're doing this completely.
And he doesn't have the hammer out yet, so it's going to get better. It's going to get better. Wear your safety goggles. We need safety goggles.
To smithereens. But I want to see if we got a couple of questions. All right. And maybe this is a question later. I see Alucard joining. Let's see. Man, we got
one thing I'll add real quick while we get questions is like, the idea of like getting to net zero, solving climate change, you're still going to make your cup of warm, delightful beverage, whether it's tea, coffee, or other hot chocolate, whatever the thing is you're into, you'll still make it in the future. But it's like all the stuff behind what you're drinking will have changed in ways that you can see, but a lot of ways that you can't see. Like you'll still have a coffee mug, you'll still have some version of a coffee maker, but behind it, like all the processes behind it will change. And that's where the engineering gets super interesting.
Well, that's
we got questions.
Yeah, for sure. And I don't want to, because I can just think like when someone says, carbon inside of it, people are thinking maybe, are you talking about in the actual material? But you're saying it's not an actual material, it's in the process of making the material. Yeah.
Yeah, so we call it embedded emissions. Some people call it embodied emissions. Okay. And it's basically like to make that coffee maker, you had to do a lot of stuff to make the plastic, to make the metal, to put the whole thing together, to ship the coffee maker to the store where it was originally bought and then used. And then, I don't know if you got it at the thrift or somewhere else, but where you picked it up. But there's a lot of emissions that had to go into all those. Nice.
You said you don't know where that's from the kitchen.
Wherever you got it, like it has a lot of emissions that were produced. And so those aren't physically like present. They're not like inside of the plastic that's right next to your arm right now. They're not sitting there, but they were produced in order to make that thing you want to use. So when you talk about decarbonizing your cup of coffee, you're not just talking about what emissions you're producing right there. So like you can make your cup of coffee on the stove with natural gas, or you can make it with electricity in a coffee maker. It's beyond the emissions that you have right in your house when you're doing that. It's all the stuff that went behind it. And so within that, we look at something called a life cycle. And so life cycle analysis, or LCA, it's actually an entire discipline within engineering. It typically sits within mechanical engineering for a bunch of different reasons. Some civil engineers work on this too, civil and environmental, depending on what school you're at, they combine these things in different ways. But mechanical engineers are like, all right, they'll say from cradle to grave, but actually we talk about, can we have an entire circular lifestyle for what you're looking at right now, where you create this thing, you use it for its life, then you recycle it, you repurpose it, you use those materials again. And where do you have emissions in that entire pathway? So behind this right now, I'm thinking about there's obviously a lot of plastic there. So plastic is mostly made with oil and natural gas. So that had to be dug out of a well in the ground, and then it had to be shipped around, probably through a pipeline. There might have been a truck involved at some point. But within each of those steps, okay, do we have natural gas, which is methane, it's CH4. It's a greenhouse gas. It's actually a really potent one that affects the climate in the short term. Okay, did we lose any of it? Did any of it leak or get out? All of those emissions up into the point where those materials were combined with other things, probably a lot of heat, to create the material that you're actually touching right now. So those are embodied emissions, all the things that had to happen up into the point that you have the thing you're actually using.
Embodied emissions. Here's a question too, because these things are a little stubborn, these little screens. it's time to get a little dirty.
Get the hammer.
But
Just
yeah,
go.
I'm definitely gonna do it. But
we're engineers.
Somebody asked like the coffee bean itself, right? Because there's a whole process there as well, right? So what is the process for how much potential, how can you go about determining how much CO2 is in the coffee bean itself? Shout out to a la carte Germany on Twitch who asked that question.
Absolutely. It's a great one. It really depends on where the bean is grown and how it is grown. So a couple of different things I would be asking just at the get-go, just coming off the starting blocks is, okay, where in the world is this created? And do they use things like fertilizers, which again are mostly comprised of natural gas? And fertilizers are great. They help us to grow the food that we need to feed people around the world. And, hunger in this world is reality for many, many people. And so fertilizers help us to grow more food, but within that, we have greenhouse gas emissions. Then I think about, okay, how much water was used? Did we irrigate those fields? Okay, well, if we irrigated them, there's probably a pump somewhere that's running off electricity. Okay, does that electricity have a carbon footprint? I'm also thinking about the field itself. Do we have anything decomposing? Do we have something going in the air there? So I'm looking at the entire process with which it's made. Is it organic? Is it not? What are the different things that went into growing that bean? Then what happens to the bean after it is grown, as it's, oh goodness, now we're at the edge of my coffee knowledge, but you've got dark roast, blonde roast, and how intense do you like your coffee? So, okay, how was that roasting done? Right out of undergrad, so this was 20 plus years ago when I was an undergrad. So my first job when I was coming out of that, about 2 decades ago, was actually working in a food manufacturing facility. And we had a 3-story tall toaster that had a lot of heat going on, and it made some really crispy cornflakes, which was awesome. I worked for General Mills. We made cereal, amongst many other things. And you think about all of the energy that went into roasting these beans, to toasting those cornflakes, and what is the source of that energy? Is it electricity? In which case, what are the power plants? Is there emissions there? Or is it natural gas? In which case, where did that natural gas come from? And within these steps, you had to get the bean from the field to wherever you're roasting it. So you have to think about transportation. Was it moved in a truck? Okay. Was that truck running on diesel? Okay. Diesel produces greenhouse gas emissions. Do we have another way to actually move those beans that wouldn't have emissions like that in the future? So you just take it step by step. It's kind of like an investigative journalist or detective story. Okay. Got to follow my bean from the beginning all the way through its life. And within that, once it's roasted, we ship these things all over the world. And so they move on trucks, they move on ships. They might, if it's really fancy coffee, it could move on a plane, but they move around the world. And so how does that happen? And then how do you prepare it? So how many beans are you using to make your cup of coffee? And that'll affect the carbon footprint of your cup. So it's just about thinking in every step of the life of this coffee bean, where are there inputs or outputs that have some type of greenhouse gas emissions associated with them? If you want to go really in depth in this, there are people who do their entire PhDs on this and actually do their entire careers on this.
So you are, speaking of that, And chat, more than welcome to your questions. I'm just getting very pretty destructive here, by the way. So don't mind.
I'm very excited.
Yes. But you work at Columbia University, right? Like,
I am,
obviously, you're doing
yeah.
a lot of labs there. What type of work are people actually getting their PhD on under the work that you're doing there at Columbia?
Yep. Yeah, so in the work that we do, there's a lot of different stuff that's going on. So at Columbia University, we have engineering departments, we have economics departments, policy departments, we have Earth's environmental science departments. So there's different PhDs that are studying lots of different things. So we have PhDs that study food sustainability. We have PhDs that study the sustainability of solar panels and how solar panels, interact with wildlife. We also have an entire center that's called the Electrochemical Energy Center. And Dan Steingart, who's a friend of mine and a colleague who works over there, what he does is he looks at batteries and figures out how and when they fail in order to figure out how to have batteries fail less, be able to store more energy and last longer, and then at the end of life, be able to actually recycle them, be able to have a circular economy where you can take all the metals that are within batteries and recover them and use them again. And so within that, there's PhDs who all do all different steps. I did a season of my podcast that was released earlier this year. The podcast is called The Big Switch. Yeah, yeah. And it's the secret, not so secret, is it's my textbook for my graduate level classes. It's storytelling about how things are made. And we went through the life cycle of a battery in the last season. And so in Dan's lab and Brett, one of his PhD students, they were looking at, okay, what are the different components of these batteries? Mm-hmm. And how do we keep them from basically blowing up, catching on fire? And how do we make them safer? And how do we increase something called energy density? So the amount of energy you can store within a finite amount of space, in order to say, okay, today, maybe I have to have a car battery that's this big if I don't have an electric vehicle, or if I have an electric vehicle, the whole floorboard is batteries. In the future, could either those batteries get me further, or could I have less batteries? So I have lighter weight and all of that. And within that, how do I make sure those things are safe and affordable, et cetera? So they study different materials, because all the things we're looking at, it's very rare that one thing you're looking at just has one component to it. Right. There's a lot of different inputs. So you think about all those inputs. So just within SEEK, so the Electrochemical Energy Center, they're really diving into batteries, battery chemistries, and how we can improve on that over time. Because when you talk about solving climate change, batteries are an incredible tool to actually help you get emissions down and get to net zero. It's a big thing. So it helps you do something we talk about, which is called decarbonization, taking the carbon out of these processes.
And that's what I want to ask you about more in just a second. Let me get my mic. But first, I have to reveal, chat, look what we got. We'll be using this coffee maker in the future. I'm willing to bet that this coffee maker is probably going to be unusable by the time we're done with it. But I want to reveal to everybody, Melissa, what we have here. So check this out. The problem that things they're built. So look what we have here. You see that?
Mm-hmm. Yep, I do. I see a lot of wires, and they're covered by sleeves, it looks like. What are you looking at? What are you seeing? What are you touching?
I see the wires, right? And then I see this sort of like heating coil that's right underneath the plate. Right? So there's a plate that's supposed to be, where this coffee pot
keeps your coffee warm. Yeah.
Right? To keep it warm. And then there's obviously, so this heating element here. The wires are attached to it. And then we even have like a little small circuit board right here. Yeah.
Nice.
So where do we go? Shout out to everybody in YouTube.
Okay,
again.
so
let us know where we go.
What do you guys think? Everyone online, we cool to go with the heating coils? I feel like we should take apart the bottom knee, because it's like there's so much going on there. Here? I see screws. I see a metal. Yeah, let's take some of that apart. Everybody good with that? Yeah, I love it. So when I'm looking at this, and man, I wish I was there. I wish I had a coffee pot with me too. I know. This is fun. This is fun to deconstruct, because I'm thinking about two things right now. I'm thinking about, one, what am I looking at? What's in there? How is it made? But two, I'm thinking already, engineer, this is what we do, right? How can I make this better? And by better, in my mind right now, I'm thinking about how can I make it easier to deconstruct, easier to repair, easier to recycle, so we can get all those metals back in the system and keep using them over time. So I'm guessing, from what I'm looking at, that plate you just popped out, I'm guessing that's aluminum, and then you've got some kind of a rubber gasket around it. It's metal. That seems pretty certain from where I'm looking.
Right, this is metal.
But I'm going to guess.
Metal.
Okay.
And then this is rubber gasket, like you said, which is kind of icky right now.
Okay.
I don't know why it got icky. But.
Yeah. Cleaning's good, which goes into life cycle emissions. You do include it in there.
So what can you tell me about about rubber? Like, what do we know about rubber when it comes to is manufacturing in carbon.
Well, we know a lot about rubber, but do you mind if I actually go with the metal plate
Oh, yeah,
first?
yeah,
And
go
I'll tell
with
you
the plate. Yeah,
why.
let's
Heat
go with it.
Heat transfer was one of my hardest classes in undergrad and grad school. I don't know why my brain did not want to get around that course. Dr. Ezekoya, thank you for your patience. You
Shout out to
really
Dr.
worked through it with
Sequoia.
me. And I did it. I mean, and I did it. I got through it. I was stubborn. I just studied a lot. But when I'm thinking about that, I'm thinking about convection and conduction. So conduction, so the heat, you've got that heating coil underneath. I'm going to guess it's a bunch of like maybe copper wires, and they've got a sleeve, which is
Right
obviously
here.
some kind of plastic derivative of some type. It's a
Right,
soft,
this right here, it's a
flexible
sleeve,
plastic.
And then
Mhm.
this is a plastic coating.
Yeah.
Right here, orange.
And you've got like plastic connectors probably that cover where the end of your wires are twisted in. I'm looking
You know
at
what's
that.
interesting? It looks like a fabric. So you got these yeah, it's definitely plastic.
Oh,
But then
interesting.
there's like a fabric. You all can see it. There's like like a fabric, white fabric. And
Did you know that in our clothes, sorry, speaking of fabrics, you know, in our clothes, most of our clothes actually have fossil fuels embedded in them. Like we have oil in our clothes.
hold
We
on.
use oil in our clothes to create the fabrics that we use today. And sidebar, there's so much when we talk about like sustainability within the fabrics that we use,
Yeah.
that we're wearing today in terms of the longevity and stuff. But going back to the fabric you're looking at, I would bet without being able to like touch it and pull it and stick it apart, that is probably not a natural cotton fiber for a variety of reasons.
Yeah.
One, because we don't want it to be flammable because that sucker is getting hot a lot. And there's electricity, there's potential for sparks and stuff. So it's probably flame retardant in some way. And so I'm betting that in that material, there's a bunch of different components, including fossil fuels. So I've got to think about oil and gas, their life cycle. Okay, how much was actually put into this? But beyond that, I want to get into the wires and the plate because like, so you've got conduction, right? Between that plate, so between the heating coils, which make contact with the plate. So the plate's hot, that keeps your coffee hot because it's making, again, contact. So it's conducting that heat into your actual, I think it's a glass pot is what I'm looking at. So this is like the money of the coffee pot, right? If your coffee is cold, you're not going to be happy. So that heating coil is probably connected in the back. It probably boils the water and also keeps the coffee warm. So that's like the $1 million part of the not $1 million coffee
You know what
maker.
because now you all don't know, by the way, this is Dr. Melissa C. Lott. She is climate scientist, researcher. You do have a degree in mechanical engineering, isn't that like your master's or something?
My master's and then my PhD is a blend of mechanical and electrical. Again, I just want solutions, so I blended all the engineering.
Listen,
and I have a degree in policy on top of it. On top of all that, I did law school.
We have a certified genius with us, people. That's basically inside Nova, do me a favor, Nova. What is it? Can you drop a definition for us? What's the class you said you struggled with? By the way, we want to get a definition for that for chat. What's the name of the
transfer.
Class? Heat transfer.
Heat
Nova,
transfer.
drop us a nice definition. Sorry about that. Of heat transfer in the chat so you all can know what they're talking about. But speaking about that, Melissa, I think some of this goo, now that I think about it, in order for the heat transfer to be efficient here, they probably put some sort of like solution, some sort of chemical transferring agent.
It's a chemical, it's a glue, it's a resin of some type to keep the contact there.
Yeah.
Because you want it to not wiggle around because you don't want, so it's convection conduction, right? So conduction, you want the contact to be happening. So you're actually conducting it through those materials. Convection, you actually have air in between, air gaps.
Right.
Air gaps we actually use to insulate lots of things. So if you think about double wall stainless steel coffee mug, there's air in between the two layers. And that's actually like a little jacket. It's a little,
so
cushion that keeps your heat in or your cool in.
So there's the type of mugs that you said has intentionally put air between two layers so that it doesn't burn your hand. That's what those paper cups.
It keeps your coffee hot, but your hand is fine. Your hand is good to go. And it keeps, or if you put a cold beverage in there, it keeps their ice going for most of the day, depending on how good of a design it is. But your hand isn't freezing and in pain when you're holding the outside of your very cold drink, effectively, because you've got that insulating layer that separates. And there's a layer of air there. But heat transfer for those online, like Dr. Ezekoya, he studied fires. He studied like how fires are created and how they continue over time. So smoldering fires, really big flames that we see. And, obviously there's safety stuff to that, but it's like, how do we think about the science of fires in order to better, more effectively control them and have them do the things they do that are good, but not the things they do that we don't want them to do, that we define as bad. So that was my hard class, man. Like, that was difficult for me. But I'm stubborn, so I got through it. And I got
Well,
all the degrees in engineering.
Well, for me, by the way, I can relate to that. Melissa, I took a class called, what did I take? Fluid mechanics. I don't know if you took that class as well.
Oh, fluids. Oh yeah, I did.
Yes. So I took that class, and that was definitely a beast for me. But I want to pause to see if there are a few other questions. Shout out to Nova, heat transfer, when energy is conveyed from one location to another via mechanisms like convection and conduction. You broke that down for us. Thank you, Melissa. Also, Chelsea Sumo, we see you. Shout out to you all in the chat. Like what you use a heat sink for. Yes, we see you. Dr. Lott, here's a question. Artsy Chickadee. And by the way, YouTube, I see you both on Twitch. But here's what we have on Twitch here. Dr. Lott, how long did it take you to get your degree? Or degrees?
Yeah. So for my bachelor's degrees, so technically it took just under 5 years, but there's two things I'll say as like an asterisk to that. One, I was getting 2 degrees at the time. I ended up having to choose at the very end, but I was studying engineering and physics because physics is cool. Like physics is just really, I just enjoyed it. And so when I had the option to add a second degree, I did that. Things changed in California and you had to choose a degree by the time I graduated. But it was 4 years and 2 quarters. But within that, my caveat is I worked through my degree. It helped me pay for school, help support some things and also get me a lot of experience. Smart move. And so I was something called a co-op student, a cooperative student with Sandia National Labs, which I was at the one in Albuquerque, New Mexico. Yeah. And so what I did was I would go 1 quarter. So it was 4 years and 2 quarters, almost 5 years for my whole degree, start to finish. But there were multiple quarters where I wasn't in school. I was actually down in Albuquerque working and getting paid, but I was working in a lab and I was learning about, to what you just said, me, like microfluidics. I was learning about how fluids flow through tiny, tiny, tiny little vessels. And I was also doing something called adaptive optics, which is a fancy way of saying I was figuring out how to like energize little things that look like caterpillars to move mirrors around. And those mirrors actually ended up being parts of telescopes that are now in space. So you want to be able to like move those mirrors around to look at what you want to look at. And so I worked on that in a lab, and that paid me money, got me experience, which then I could take back to school. So it was just under 5 years for my bachelor's. My master's, I got 2 masters and I did them at the same time. So a master's degree, depending on where you do it, it'll take 1 or 2 years. A research master's where you do research takes 2 years. By doing 2 at the same time, it took me 3 years total to get 2 degrees. So that was 3 more years. Then for my PhD, and I worked in between all my degrees, so I didn't go straight through. So I worked after my bachelor's, and then I worked after my master's, and I worked the whole time I was in all my degrees. So I had a lot of jobs, had a lot of hats. But my PhD took me about 3.5 years. And that was partially because by the time I got to it, I had my master's already. And I basically went right into something called qualifying exams, where you prove out you've got the base knowledge. And if you pass that, then you do a research proposal, you pass that. And then I was working like 3 side jobs and I put my head down and just got it done because I knew what question I was trying to answer. And I got lucky in some ways in that my initial approach, most of it ended up working out. I did have to adapt, but like a lot of it did work, which wasn't totally surprising because I'd use those approaches in my work outside. But that's the long story short. So let me add, let's just call it 5 years. I'm gonna do some easier math. 5 years plus 3 years, 8 years, 3.5, 11.5 years of like education while I was working. And this was in California, Texas. And then I did my PhD in the UK. So in London.
That actually,
and I know it was engineering, to your point, Nee. It was engineering. How long did it take you to go through school?
No, that was very similar to my experience, except for my PhD really did take the full time because I did a master's too, but it took me 11 years total. So I did undergrad, and by the way, I want to ask you about this too. We're gonna come back to it because I'm structural engineering. Chat, YouTube, I am structural engineering. We build bridges. We do a lot of concrete and steel, which I understand has a huge carbon footprint.
Huge.
Yeah, so we can get to that in a second. But anyway, I did structural engineering. I also then moved from that into a master's that took another 2 years. My undergraduate took 5 years because I had 2 degrees. I did dual degree. Yeah. Then 2 years of master's. And then I came and started my PhD, which took another 4 years. So 5, 2, and 4.
It's really similar.
11 years. Yeah.
It's really similar. Yeah. And I know some people have done like part-time PhDs, so it takes them longer, but they're working full time and they're, doing their PhDs as many hours as they can. And it takes time. Same with masters. There's all different types of approaches and flavors. But yeah, I think I was looking at iron and steel the other day, me to your point, and like iron and steel is almost 7%, or it's just over, 7% of global greenhouse gas emissions.
Whoa,
like
steel?
Iron
and steel. So like those, all right.
Iron and steel.
I've heard this somewhere and when in preparation for this interview, and I was like, man, we've got to do something different. Let me ask you, before we get to that, let me ask you this question. If we're doing this coffee maker, right, and we're talking about all of the, you use the term embedded carbon.
Yep. Mm-hmm.
What is the way?
Embedded or embodied, yeah.
Yeah. What is ideally the way to reduce that from both either the production side or even like the disposal side?
Mm-hmm. So on the disposal side, you want to make something that can be repaired and recycled at end of life. So you want to make it easy to take apart. So look how much time and energy you're having to spend taking apart this. It's fun.
Yes,
okay. We're engineers, so we enjoy this. But if we had to hire people or pay people to take apart every coffee maker that's out there, so we could do a bunch of things to improve it, but it would just be a lot of time. So you want to make it simpler from the beginning. So right now, recycling this, a lot of it might just be about crushing it and then putting it through a lot of different processes, including some chemical ones to separate out materials. Mm-hmm. Or in all likelihood, this would end up in a landfill. So how do we prevent that from happening? How do we recover everything we can recover from the system? And so that's about intelligent design, designing for that end of life and that recycling, so we can improve things there. And there are some countries in Europe that actually have a right to repair law. And what that says is these things have to be built in such a way that you can repair them. So maybe not you personally, but you could take them to a shop, which means that the company has to make replacement parts available. Mm-hmm. And you have to be able to take this apart without completely breaking it to the point that you couldn't put it back together again and use it as your coffee maker. So it's things like that. But during the life cycle, it's like, how do we make it as efficient as possible? Because I don't think, tell me if I'm wrong, you don't care about how much energy it takes. You care that you get a nice cup of coffee out, right? So if I can do that cup of coffee with less energy, that's going to be good for everyone, because you're using less energy, you're putting less strain on the grid, that's less power plants, that's less need to get the fuels that power those power plants, that helps everything. And then I think about the individual materials. So how do I make every material that's in that? I think about replacements, if we have easy replacements with more sustainable products, but how do I make it so that I can create, oh man, sorry, I'm looking at the middle of this. I want to take about
I know. I see
red
that.
wires.
What should I do? What do you want to do next?
Well, I want to see if we can you pull apart where the red connection is? Because that's going to be the heating coils, I think, that go up to the top part, which from memory is called, I think this is my correct memory. It's called like a shower head, where the water comes down and like gives the coffee a shower to make your cup. Yeah. That's going to be, I think, but I'm looking at this. And then it connects also to the heating plate at the bottom.
This one right here, I don't know if it's like an input output, some sort of thing, or a signal, because this right here, this is more of an mechanical engineering connection. Like I see where this is attached to, I don't know if you all can see that, but I'm not sure what these are, but these are things that seem to be signal or connected to the shutting of the top.
Sensors or something. Yeah. So the top is down, it will start boiling.
Right.
So there's a sensor, there's probably a switch in there. There's probably a switch, because it doesn't want to be boiling with it open. Some of them that are more basic, they might not have that switch, but this might have a switch in it. But the other one, I'm guessing there's going to be wires in there, because we got to heat that water that's in the top, right? We got to make that hot. So there's got to be a wire that's bringing electricity.
Okay.
It's empty too.
So here's the thing. It's connected to the coil. It's definitely connected to the coil. See, here it is. That was going through.
Yeah.
There are no wires directly in this part. And for those who are joining us, this used to be a coffee maker, by the way.
Okay.
There are no wires connected directly to this top. So I think maybe there was just sensing if it's closed, that somehow, some way, right? Because these two circuit boards were connected, by the way. I disconnected it.
Yeah.
But somehow sent a signal that activated the heating element. You know what I mean?
So when you pulled that out, did you so either it was a sensor, or I actually took apart, it wasn't a coffee maker, but it was a system that boiled water. It was a kettle. And there was also a water line in there, but those are that's just one more point of failure. So like, if you can avoid that, you probably do. But that doesn't look like a water line to me, but I wish
quite.
I was
Well,
there. I want to like take this apart.
I know.
I'm
No,
so-
I'm going to keep going. I'm going to keep going. We have more time. And by the way, you all
Well,
are
if
welcome
that
to
was
ask
a-
questions. I'm sorry if I missed anything. Oh, wait, Melissa, I'm sorry. We're jumping around so much. This is a lot of great stuff.
I
and
know.
I'm sorry to keep you going. I'm like
Yeah.
engrossed in this.
Yeah.
But I do want to make sure I get some chat questions in while we're here. All right.
Absolutely.
Let's see. There's one question around. Let's see. Taking the coffee maker apart. Yes, thank you, the Opal guy. Appreciate answering the questions. The Miss Damas. Shout out to Damas. We see you. 1996. Does human-centered design play a role in? Am I asking the right question? Yeah. Does human-centered design play a role in creating items that are easy to take apart and put back together again? I guess you already said that. Like, should it be easily taken apart by professionals, or do we want to make this to where every user of the product can just simply take it apart? And I don't know. I guess there are safety concerns, perhaps. Maybe that's what that's coming from. But go ahead. What are your thoughts?
I mean, it's in between, right? So we can design for safety. So you can make it so that if the thing's plugged in, there's some kind of system that makes it so that you have to unplug something. Maybe you have to remove the power cord before the box will open up. So you can design systems that have fail safes that prevent you from doing the dangerous things. We also have fuses in our house. You don't want to test your fuse with your body, but we have safety things in our houses as well that help protect us from these things. But let's break it down for a minute. So human-centered design, it's not just about like end of life and being able to deconstruct it. It's about how, users will use these projects, what are their needs and requirements. And so, I am lucky I've got hands that can grip a certain way that is pretty standard average majority of folks, but it's like, how do we design a coffee pot that can be used by everyone who wants to make coffee? And then how do we do it so that it can be repaired over time? So there's lots of different steps to think through in this. So within the actual design of this system, there is a big argument for saying we should be able to take it apart as individuals. And I say that for two reasons. So yes, there's the safety concerns. Let's say we can design fail safes that make this extremely hard for you to be harmed by this. But two things. One, it makes it cheaper for you to repair yourself, right? So we all know if you have to hire a contractor to fix something in your apartment or your home, whether your landlord's paying for it or you, but it's going to be more expensive, then you could say, maybe I could just do this real quick, as opposed to getting people in quotes and all that stuff.
Right.
But also, I used to live in Japan. So I worked at the Asia Pacific Energy Research Center, which is in Japan. I lived in Europe before then and the US for the majority of my life. But in Japan, they recycle the vast majority of their waste. And so within that, you do kind of take your trash apart. So when you have a cardboard box that has tape, you're removing the tape, you're removing the labels, you're breaking down the box, you're folding it. In Tokyo, you're tying it up with twine in a thing, and then there's a whole system to take it. So if you make this hard to take apart, what you're doing is introducing a really difficult step in the recycling process, like I was talking about earlier. So if we think about the users of this and we think about it as more than the person making coffee, you want to make it easy on the person who takes it apart, whoever that is, if it's a professional in a recycling center, or if it's a user and your recycling system requires that you take things apart and put the plastics in the plastic bin and the metal in the metal bin and the glass in the glass bin. It's a ton of plastic. And there's reasons for that. It's cheap to make, it's sturdy and durable, and it's light. So when I'm shipping it around, if that coffee maker, two things, if that coffee maker weighed like 50 pounds because it was all metal, it would be difficult for many users to use it, but it would also be really expensive to ship because the amount of fuel that you would have to use to move it around would be so much more.
Okay. Thank you so much. Thanks for that question, Damas. And people are coming on, but the overall of this R&D will make the thing more expensive, right? The inevitable question. How much more money will we spend if we did this?
It depends. So, and this is a tough one, and there's a lot of equity issues embedded in what I'm about to say. So I'm just going to put that there, and we can go down the rabbit hole as you want. But within this, you can design something that's more expensive up front, but cheaper to use over time. So over the life cycle, over the life of this appliance, you actually save money. But maybe up front, you got to pay another $5, $10, $20 because all the materials are improved, they're better, the whole system is more efficient, it uses less energy. But that's the thing, you may have to pay more upfront, but actually you'll save money over time. The other thing is, though, to your question, like getting to net zero and solving climate change, getting emissions out of systems.
Right.
In some of these processes, like for the plastic, we might go from using oil and gas to using, let's say, bioenergy, so plant-based energy.
Right.
There's a lot of limitations to it. I'll leave those aside for the minute, but let's say we do that. It might be more expensive. It could compete with other things we want to do. Okay, so let's think beyond that. What are the different materials that we can use to still have a lightweight, durable, easily cleanable material that doesn't involve emissions, and so probably doesn't involve the use of as much or maybe any fossil fuels? Some of those things we're still inventing and creating in the lab. We're still experimenting. We're still figuring out how to make chemicals and not just petrochemicals. There's a lot of different things we're still creating. And so until we create it and then commercialize it and scale it, that stuff is expensive. But like right now, I'll give one example. If you go to like, you need a hot water heater and you go to the store and you'll see those Energy Star efficiency labels on them. And what they tell you, like, over the course of a year, this one's going to cost you, $1 and this one's going to cost you $3. It's a lot more than that, but there's a difference between the two. The one that costs you $3 a year to operate probably is cheaper up front, but then over the course of its lifetime, you'll spend a lot more on energy. And so it's a balance. And it's also who has the privilege to have money up front to be able to pay more up front to save money over time.
That's a good point, and that's a good question. Shout out to you all. That actually comes back to, the industry that I know very well, civil engineering, constructing. You said that iron and steel, that's about 6% of our carbon emission. That's crazy.
Just over 7%.
So that's iron and steel. And then concrete is another whopping estimate, plus or minus?
So cement is something like 3%, but here's an interesting point of emissions, of global emissions, but here's an interesting point in it. And I'm actually trying to pull, so you have process emissions and you have combustion emissions. So I'm just going to pause there. And if somebody is online and goes to Our World in Data, and let's look up that number, because Our World in Data is awesome for taking all different types of data about where emissions come from, and they put them in really accessible like pictures and graphs. So if somebody pulls that number for me,
shout out to chat. We got a great community, and we got Nova on our side too.
Absolutely.
So everybody can drop that.
And totally. And those websites, they'll give you, what are you into? What do you work in? Like, I have a student who works in the flower industry. And so she was learning about transportation emissions and agricultural emissions, because she's like, you got to grow the flowers. But that aside, cement and concrete actually have two things going on. So one, this, Nee, like in the process, how do you make this stuff? You're actually cracking limestone rocks.
Limestone. Okay. Yes. Yep.
So you're not burning anything, you're cracking rocks. And when you crack rocks, you are releasing greenhouse gas emissions. Yes. So that's a process emission. It's not a combustion emission. You're not setting something on fire. But then, so the emission sources are different. So when you're making steel, you use a ton of heat at different points, and that heat has emissions with it. And to make that heat, you're probably setting something on fire. That's combustion emissions. But process emissions, that could be cracking limestone. It could also be combining different things to create a chemical dye to make my shirt black, your shirt black, whatever it is you're creating. So there's two different types of emission sources, and only one of them goes away if you stop burning things. You still have process emissions. So for cement, like the solutions to decarbonizing, to taking the emissions out of cement, are different than they are for steel, because the source of the emissions is different. So you'll do different things. Your solution set is very different because the source is different. Does that make sense?
No, that makes a lot of sense. And I guess the idea was, okay, how can we make the process more efficient, right? And then also you begin to think about when we're releasing carbon into the air. Like, I think there's a way that you can capture it and put it back underground, right? Like, there's like a process. It's not widely adopted, but there's like a process where you can, I can't remember the exact name, Nova, I think it's an acronym, carbon capture and storage, CCS.
And you can call it CCUS, where you actually utilize and store it. So use as much as you can, use it as feedstock. But okay, you just picked up the massager. Can we do something that I've been thinking about this whole time? Which is,
tell me. By the way, I just organized
right?
everything. This is plastic. These are like metal. This is glass. This is rubber. Like, what do you want? What we got?
So, okay, within each of these steps, and then I want to go to the massager before we lose this thread, but like in each of these things, so I've got glass, I've got metal, I think I have aluminum, and I'm betting I've got some, I think the screws are steel. I can't tell from here. They could be stainless steel. They could be, they could be something else, but it's a metal of some type.
Right.
But what I do is I go and I say, okay, how is aluminum created? So where do we get the ore? What parts of the world? How do we refine it? How do we then create it into the thing I want. So in the case of, that heating plate or that band that was around the top of the actual pot where you're putting your coffee in, the glass pot. So today, I make aluminum by taking a bunch of ore, which includes a lot of aluminum oxides and a whole host of other stuff. I refine it to make aluminum. Then I do something called smelting, which is basically you're heating stuff up and you're melting it.
Smelting.
And then, smelting. But in all this, you're using energy at different steps. How would I do that differently if I didn't want to emit emissions at any step? And within that, on the cost thing, if I can't eliminate emissions, how do I capture them? How do I offset them somehow so that the balance, again, between what I put in the air and what I take out is zero? Maybe I can't get what I put into the air to absolute zero, but then I can take something out somewhere. So I think about those steps, but I do it for every single material there and every single manufacturing process. So for those chips, those circuit boards that you got right there, where are they made? Who makes them and what goes into them? There's a bunch of different metals in there. But there's also a bunch of different processes, very fine-tuned, highly skilled processes that go into that, probably highly automated. There's probably a lot of electricity use in that. There's probably a clean room involved, maybe at some point, definitely if you were a chip fab, you would do that. But how are you using energy? Where are emissions coming from? But here's what I want to get to with the massager. So no offense to your coffee pot. It's cool. It's got a lot of plastic. If you made that coffee pot a lot more expensive, you might have a lot less plastic involved. And you would have other materials that are more durable, perhaps, but also more expensive. So homedics in my world is really fancy, but I'm kind of wondering, if you open that up, are you going to see a ton of plastic inside, or are you going to see a bunch of metal? And that's a trade-off, because the metal and creating it is probably more expensive. It's more expensive to move around. But okay, before you fully open it up, how heavy is that thing being?
Is it heavy? And I don't even know that I'm gonna fully open this up, to be honest with you. That's why I was just trying to go ahead. Fine. But this is heavy. This is heavy. Just to show this to the people. This part right here, like, I don't know. It's a low key weapon. All right. So,
who needs a baseball bat when you have a massager? No, but in there is probably some kind of a motor that's moving around the two different massage things. And the two, what do you call them? Massage pads? We'll go with that.
Pads. Yeah, we can go with it.
Pads, the little things that, get the knots out of your shoulders.
Right.
And like behind that, I'm guessing is a good amount of metal in that motor and like in the stuff that's inside of it.
We got an agreement.
If it was cheaper, it might be lighter, but then the materials that are used would degrade faster. And so the whole thing would break faster. So this goes back, it's the same thing. You're probably paying more upfront for this, but then it might last longer and it might be higher quality and produce a better, shoulder massage.
Right.
Where the coffee pot, maybe, that fancy, expensive, and very heavy thing that's on the counter at your local coffee shop.
Right.
It's expensive, but it produces better coffee? ? Says the non-coffee expert. And then also maybe it lasts a lot longer and you can make thousands of cups of coffee every day, where if you tried to put your home coffee maker through those paces, it would break pretty fast. So these are the trade-offs. More money up front for better, defined as more durable materials.
Right.
It might be heavier, uses more metal, but then it lasts longer. And so over its lifetime, it might be, better for your purpose, whatever that is.
Life cycle costs. That makes a lot of sense. Hope you all are getting that. By the way, you're getting some agreement in the chat. Shout out to everybody on YouTube and on Twitch. We see you. We come to you every day here on Building Stuff with Nova. I think you mentioned something, and maybe you can, tie this into my next question. But you did mention briefly about, equity and things of that nature, which I think is really important, because when you're thinking about life cycle, again, I think that sometimes people are limited by their resources to pay that upfront cost, right? But there are other people who also can't afford it, and you want to sort of like make sure, as we push for, sort of this zero emissions world, right? Net zero. When we push for this circumstance, we want to do it in a way that's equitable, but also keeping in mind the why, right? And that's one of the things I would love for you to kind of touch on, so everybody can know, because you clearly know a lot about this. You studied, you spent over a decade in school, like myself, getting the solutions, gathering your own, toolbox, if you will, to be able to address this issue. And I'm just curious if you can share a little bit more about why this is so important and why those of us watching this, regardless of where we fall, should care about it.
Yeah. So when it comes to climate change, what we know from the science is that even in the most optimistic scenarios, so like for those who studied engineering out there, in our sensitivity bands, like the best case, lowest cost, like the bottom, the least risk, we know that even in that scenario, climate change has huge negative impacts on our health and also on the environment that relates to our health, but also feeds our economy. And all these things are tied together. So our health and our well-being is massively negatively impacted by climate change. What we also know is that given technologies that engineers and scientists have been creating over many, many decades, we can get down to net zero emissions in a way where it's cheaper to pay for these things than to sustain those health impacts, those impacts on our health and well-being. So the difficulty is we pay for one thing in our power bills and in our bill at the store when we buy, whatever it is we're buying for our lives. We pay for the other bill in our health insurance and our healthcare system. So it's like, and in our insurance bills, as we see more extreme storms, more extreme heat waves, more extreme cold snaps, and all the impacts of that. So climate change is really, really expensive for our health and our well-being, and therefore our economies. And so when we talk about decarbonizing, the equity piece of it is, okay, as we move to net zero, we know we're going to have to make some upfront investments. If we do it right, the costs, it's still a massive savings compared to the cost of all the negative health and environmental impacts. So it's still a savings, but how do we design the system? This is probably a policy question. How do we design the system so that, one, those who are already in a tough place and are struggling to pay their power bills or struggling to afford life and to be healthy and to be able to do the things they want and have life opportunities in life, how do we make sure they're not worse off? How do we make sure that they are in a safe, good place? But also that we're moving as quickly as we possibly can to actually solve this. So how do we do that? How do we move quickly while making sure that we don't have people falling into tough places, which results in us actually not moving at all if we see that happening?
So we're paying for it one way or another at the end of the day.
And we're paying a ton if we don't move quickly. Like if we don't move really quickly to get emissions down, we will pay way more. And I mean, we're sitting in the middle of a hurricane season. I don't know if you've been reading about it, but it's intense.
I definitely know some flights have been canceled over in my parts as a result of where people are going to because of the season we're in. And it matters and it hits on so many different levels. I can't thank you enough. Y'all got to give her some love. Show Dr. Melissa some love for sharing that. And I want to give a quick shout out to the people who are curious. You said there is a motor. That's absolutely what that is. Shout out to RC Chickadee for putting that in there. There's a motor in here. And this big circuit board that I just ripped to shreds. To try to rip it open.
I don't think you're going to be able to put it back together. Deconstructive analysis.
Exactly.
Deconstructive processes.
Exactly. But Melissa, you've been so great. I thank you so much for being a guest. Shout out to everybody on YouTube for hanging out with us today. Everybody on Twitch, hey, the building committee, thank you for being with us yet again. For all of you, in case you didn't know, I just want you all to know we got a lot of cool things still coming, even later even next week, right? So tomorrow is a holiday. We're going to take our break for the holiday. Many people are celebrating or taking their rest in whatever way they choose to. And then on Friday, we also will take a break. But here's our schedule on the screen, everyone, for next week. Yes, we're going to go back to Kerbal Space Program, get into aerospace engineering, build our virtual rocket. Last time we were able to get into space. Now we're going to see what we can do after that. Then we're going to bring back, for those of us who are interested in that escape room, Mike, our trapologist, our guru, is going to join us as we ideate on how we can implement some of these ideas and concepts into our 4-day escape room that will be our finale this fall on Building Stuff at Nova. And then, of course, we're going to have a few more days of playing Kerbal Space Program. We have a virtual field trip. That's right. I'm going to be sharing with you all, my friends, the lab where I spent a good portion of my 11 years in school studying a lot of massive, large-scale structures and testing them in the North Carolina State Constructive Facilities Laboratory. So make sure you join us next Thursday. And then we're going to look at another game. We're going to try to experience another game, Melissa, and those of you who are new to this channel, of how we can game but also explore many of these building stuff. And today, really deconstructing stuff, principles and concepts with you right here on Building Stuff with Nova. So if you enjoy that, make sure you go over to Twitch, or if you're on Twitch, hit follow so you can continue to hang out with us, and make sure you join us again next time on this channel, Building Stuff with Nova. This is Dr. Nee signing off. Take care, y'all. Peace.